Hello, and welcome to Physics for Play. In this episode, we will continue exploring the physics of the damped driven harmonic oscillator. Let's get started. So, to recap, we've been looking at forced harmonic motion and resonance. We set up our equations now with a driving function, and we have, over the last couple of videos, looked at both solving and how to solve the forced and undamped oscillator. We've looked at how to solve the forced damped oscillator, and we came up with the particular solution through a lot of work and a lot of algebraic manipulation. We were able to come up with the equations for the amplitude of the solution and the phase shift of the solution, all based on our initial guess, x equals e to the I omega t minus delta. We are going to continue exploring the solutions we had, which looked like this. When you plot them out, we're going to continue exploring those solutions today to get a little bit more of a sense of what's the physics at play here. So I've taken the liberty of going ahead and copying down the solutions. We've already seen them in the last video. Now, a question that you might wonder is, all right, well, we can see that the amplitude is peaked near the resonance frequency, but where exactly is that? And that is easy enough to find, because what we can do is we can just look for where this peak is. So I can just take the derivative of this amplitude function, set it equal to 0. I know that's from calculus, that's where you find where the max is, because the slope right at the peak goes from positive to negative, so that's going to have a 0 slope. So we can take a derivative in this way. We're going to hit escape dt, escape, and that gives me the shortcut for a derivative. And I want to take the derivative of a as a function of omega, and I'm going to take that derivative with respect to omega. And I want to find where that is equal to 0, so I type in the double equal sign, and I do that. Oops, I need to let me quit my kernel because I've got a bunch of variables defined, and I want to keep this as general as possible for now. So we'll do this in variables. So you see you get a little bit of nastiness going on there. I do want to actually solve this, though. So I'm going to say that we want to solve this for omega. And I don't want to waste any time with any nasty algebra, so I'm just going to tell Mathematica that as soon as you're done with this, I want you to go ahead and do a full simplify on that. And when I do, you can see I get several different solutions here. One of them is that you have a solution at omega equals 0, so your slope is 0 over here. That doesn't really help us out too much because that's not where the peak is. Nor is the peak this negative value coming out of the square root, so I don't want that one. Instead, I am going to want this to be my resonance solution. So I'm gonna say that omega r, the r is for resonance. This is my resonance frequency, is equal to just what we had over here. So that's square root minus gamma squared over 2 plus omega naught squared. Now, something important worth mentioning. Back in the first case that we looked at, where you had resonance with no damping, you have a driving force with no damping, the resonant frequency was just equal to omega naught squared. That makes sense, because if I set the damping to 0, this term goes away. I get I'm left with the square root of omega naught squared. So the resonance frequency is just omega naught. That doesn't quite work when you do have damping, because obviously you have this term showing up. So your resonant frequency is actually, when you have damping, it's actually a little bit less than the natural frequency that the spring would vibrate at to begin with. So when we're plotting this, we can do a few other things. We can also figure out how big is the resonance peak, because I can just plug in the into the amplitude as a function of omega. I can plug in what that resonant frequency is, and you can see this tells you what your maximum amplitude is. We can, what else can we do here? I'm going to make sure I document this a little bit. This is your peak amplitude. Another thing you will often see defined for resonant systems is this thing, this variable Q. Q is called the quality factor. It's basically a measure of how good of a resonance do you have. And its value, I've seen a few different definitions of it that aren't always consistent, but its value is the resonance frequency divided by the damping coefficient gamma. So I'm actually going to put in a few different variable definitions here so we can start plugging in numbers. I'm going to define F naught to be 1. I am going to define the damping constant B to be 0.5. Spring constant, we'll make that 1. The mass, we'll make that 1. Recall that omega is equal to, what's the keyboard shortcut for square root? We'll do square root K over M. We've got gamma is the damping constant B divided by M. So we've got a few different parameters in here. We've got a quality factor. I'll comment these out. What you can see with this is if I have a whole bunch of damping, that's probably too much damping. If I have a lot of damping, I have a very low quality factor, so 0.85. If I have very little damping, I have a very huge quality factor, and that it's basically a measure of how sharp your resonance peak is. So it'll actually be helpful to take a look at this. I'm not going to go through the full. I'm going to copy some code here that I put together beforehand, and it's basically just some code that's trying to get the graphics to look nice. Make nice plots. I'll hold it here. If you want to pause the video and copy this down, you certainly can. But I'm going to define my maximum amplitude here. All I'm doing here is making some nice plots where we can see a little bit more of the physics. We can see the physics a little bit easier. So we're going to run this. We're going to spit out our quality factor, and we're going to see what the resonance peaks look like for different quality factors. So here's a really sharp resonance peak. You can barely see it. The delta, which we had before the phase shift, almost discontinuously jumps at the resonance peak value. This is the case where I have a really tiny damping coefficient, just a little bit of damping, almost nothing, almost no friction there. Very sharp peak, very big amplitude. And right when you get from one side of the peak to the other, you switch phases. So you go from pushing in phase to pushing out of phase. And the resonance peak and the natural frequency are pretty much exactly on top of each other. Let's add a little bit more damping and see what starts to happen. So we're going to increase our damping coefficient B to 0.1. And you can see this starts to spread out a little bit. My resonance peak is no longer as sharp. My Q value goes down to about 10. And my phase no longer discontinuously jumps from one side of the resonance peak to the other. You can see you more gradually go from in phase to out of phase. Let's put a little more friction in and see what happens. Oh, now you're starting to see something interesting. So again, the phase shift is changing, but even more gradually this time. My peak is even broader than it was before. And now all of a sudden my resonance peak is different than the natural frequency of the harmonic oscillator. My Q is quite a bit lower. It's only about 2 now. We can keep going with this. We can keep spitting out larger and larger damping constants. Resonance peak moves even further away. Q factor gets even smaller. Let's see. At a certain point, something bad is going to happen. And you can see it here. Our resonance peak has, our resonance frequency is given by omega naught squared minus gamma squared over 2 square root of that. Well, omega naught is square root k over m. K is 1, m is 1. So square root k over m is also going to be 1. So as soon as gamma squared over 2 is equal to 1, this resonant peak is not going to be there anymore. It's about to turn into 0 and then go and become imaginary. And that will happen at, looks like gamma is square root of 2. If I'm doing my math correctly there, square root 2, yeah, so that'll be square root of 2. So if I plug in, you'll see resonant peak goes bye-bye. Q value goes to 0. Nothing is there. If I make it just a little smaller than 0, well, looks like I've got like just a little teeny tiny baby peak in there. But to really see it, you got to be somewhat different than. You got to have a larger distinction. You've got to have a bigger, a little bit less damping. And you can see my peak starting to come back there. So that's where we get the physics of this this resonance phenomena. There's some interestingness here. It's not just push at the resonance, push at the natural frequency, and you get a peak. There is quite a bit of subtlety here, both in terms of whether you're in phase or out of phase. How your resonance peak is shifting. How big, how sharp is that resonance peak. And we can describe this also just by using this quality factor variable. I'm going to stop here for now, since I think we've covered a bit today. Go ahead and like the video if you liked it. And if you would like to see more of these, please click subscribe.